Okay, so today what we're going to talk about is the electric field. Okay, I'm not going to get into the calculations of the electric field yet. I think I'm going to do that in class with you guys tomorrow. However, I think I'm going to tape that one as well so you can go back and refer to it. And I'll post that on the website as well tomorrow. This one is not as nearly as complex as what I was originally thinking. I want to do this first, make sure you understand it, and then when I see you again on Friday, we can hit some more of the more intense things. So anyway, first of all, what is an electric field? Okay, well, let's think for a second. Well, what is a gravitational field? Okay, we know that that mass is something that distorts. We talked about it the other day. It distorts space and time. Okay, and it affects the mass, any masses that are around it. So now, the gravitational field exists in any region where mass will feel a force, simply because of its mass. Okay, so now we know that mass will create gravitational field, okay, like the Earth creates its own gravitational field. We know that mass is affected by a gravitational field, okay. These are all attributes. I know it doesn't get to the essence of what a gravitational field is, but one of the things that we have to do with this is kind of look at the attributes of a field before we really can kind of get a feel for what it actually is. Let's see. Similarly, anything with mass will create a gravitational field. Okay, the Earth creates a gravitational field. I could create a gravitational field. Mine is much smaller than the Earth. It's still bigger than yours for the most part. But I'm affected by Earth's gravitational field. Earth is affected by my gravitational field. Okay, those effects are the same. Okay, the force is the same on both myself and the Earth. It just so happens that the Earth has a much larger mass, so the acceleration of the Earth is significantly smaller, by 10 to the minus 20th or 25th or whatever it is, compared to what my acceleration would be. Let's see. Now, along with that, from a large scale, okay, we're affected by Earth's gravity. The Earth is really affected significantly by the Sun's gravity. The Sun is affected by Earth, but not nearly so much as the force is the same, but the effects are much smaller on the Sun because of its much larger mass. Now, what exactly is a gravitational field? Well, if we go back, and I use this gravitational field because we have the sense of what gravity is. So I'm going to come up with, I'm going to call this the gravitational field, I'm going to call capital gamma. Now, the reason why I use gamma is because we use little g for the acceleration due to gravity. We use big G for the universal gravitational constant. So I'm going to use gamma because, well, it has kind of a G sound to it. And it's, we'll use that for gravity. Okay? Now, the gravitational field, okay, we'll say that this is the gravitational field. Now, gravitational field, it's equal to the force of gravity acting on an object divided by its mass. Okay? It's a force of gravity acting on an object divided by its mass. Okay? So now, think near Earth's surface. Gravitational field that's created, well, let's just think about near any mass, first of all. Okay? If we look at the gravitational field, force of gravity, okay, big G, we'll say that this is a big M, times the mass that the mass that's in the gravitational field, divided by the distance between their centers squared. So now the gravitational field would equal, and I could put, make this a vector or whatever, gravitational field. Okay, I'm going to look at the non-vector form. We're going to look at the magnitude divided by the mass of the object in the gravitational field. G big M over R squared. Okay, so this is the gravitational field that's created by a mass M, big capital M. Now let's think about near Earth's surface. The force of gravity near Earth's surface on an object with a mass M is equal to, we know it as mg. In fact, I will make this a vector. It'll be, we can look at this one pretty easily as a vector. Okay, if I say I want the force per unit mass, well, near Earth's surface, the gravitational field is equal to acceleration due to gravity. Now, gravitational field is a little bit easier to analyze than the electrical field because it is per unit mass. And if you take force per unit mass, you get a quantity that we understand, which is acceleration. So this right here, this is the acceleration that a mass would experience given, given that it's in a gravitational field. So a gravitational field, it's a quantity that we actually do understand. It's the acceleration. Now, the electric field isn't quite so nice because we're not looking at the amount of force per unit mass, which we know gives us an acceleration. We're looking at what's called the force per unit charge. So I'm going to start off here. We're going to define the electric field as the force, electrostatic force per unit charge. Okay. As M creates this gravitational field, and as M is affected by the gravitational field, charge will create the electric field, and charge is affected by the electric field. Okay? So just like mass both creates and is affected by the gravitational field, the charge both creates and is affected by the electric field. Okay, so now, why is this useful? Well, if we know the amount of, given a certain amount of charge, okay, that we have, if we know the electric field that exists in a certain location, we can predict what the force on that charge would be. Okay, so now we could have, okay, the electric field per unit charge. We could rearrange this and say that the electrostatic force on a charge is equal to that electric field times the charge. Okay? So if we know the electric field and we know the charge, we can predict what the force on that charge is going to be, which can be terribly useful. Now, as we get into this, I want to point out that the electric field is a vector. Okay? That means that it has direction. Okay? The direction, and this is definitely important to get in your notes. The direction the electric field points is the direction a positive charge feels the electrostatic force. Okay, electrostatic force we talked about the other day. That was at 1 over 4 pi epsilon naught Q1 Q2 over R squared. Okay, so the electric field is the direction that a positive charge experiences an electrostatic force. Okay, now a negative charge would experience a force in the opposite direction. So now, this is why gravity is a little bit easier to study than the electrostatic field. Okay? If I put a mass in a gravitational field, I know the direction, no matter what, that the mass will experience its force. If I take this mass, this thing has mass. It's near Earth's gravitational field. I drop it, it goes down. I take anything else, it goes down. I take it, ooh, I want to be careful, that's very expensive. Okay? Anything I drop, anything with mass, it goes down. Okay? Because the gravitational field points down. And masses follow the direction of the gravitational field. Electric field's a little bit different. Okay? It points in the direction that a positive charge would go, but a negative charge goes in the opposite direction. Okay? It's a fundamental difference, one of the fundamental differences between mass and charge. Mass has only positive values. Charge can have both positive and negative. Okay? And again, positive charges for ordinary matter, and there's other things that have positive charge. Okay? Other subatomic particles that have positive charge. But the things that we typically experience are protons and electrons with negative charge. Anyway, okay, electric field is direction. Okay, so now we want to look at how we create the electric field. Okay, and in order to do that, we have to look at the electric field, the direction of the electric field that's created by different charges. So now, let's just say I have here a positive charge. I want to look at the direction of the electric field that's created by this positive charge. Now remember, the electric field points in the direction that a positive charge would experience force. So if I put a positive charge right here, called a test charge, okay? Put a positive charge right there called a test charge. And I released it. Like this is fixed in place, this is free to move. What direction would it experience a force? Go to the right. So if I put a positive charge right here, go down, right here, goes to the left, here, goes up. Okay? And from there you can kind of fill it in. Okay, positive charge here goes out, 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 out. Electric field points out radially from anywhere near that positive charge. Okay, it points out. Okay, I can do the same thing with a negative charge. Okay, if I put a negative charge over here, they're completely isolated from one another. Okay, if I take a negative charge right here. Okay. What's the direction of the electric field that this negative charge creates? Well, if I'm right here and I'm a positive charge, and these test charges are always, these test charges help us figure out the direction of the field. Okay? If I put a test charge right here, remember it's always positive, what direction would it experience a force? Okay? Well, if it's positive, this is negative, that's attractive. Goes in. If I put it over here, goes in. Over here, goes in. Over here, goes in. Okay? And then, just like before, you can kind of fill in. Okay? And that is the electric field for a negative charge. Now, obviously things get a little bit more creative than that, beyond a single point charge, either negative or positive. Okay? Something I want you to do for homework. Okay? We have electric field. Okay? Two unique situations. Okay, isolated from up there. I've got a positive charge and a negative charge. I want you to draw what the electric field is going to look like between this positive charge and the negative charge. This is, I'll call this 1A. B, okay, completely separate. I want to know what the electric field looks like for two positive charges. Okay. So create the electric field with a positive charge, two positive charges, and with a positive and a negative charge. Now, there's different ways that you can try to figure that out. I would try to figure out what these are individually first. Before you go, it's in your book, you can find that. So if you go look in your book, you can do this and you can see what it is. Additionally, okay, sorry, I was pulling up a website. For some reason, this is blocked. This website is blocked. I'm going to cut and paste the website into the blog post itself. But you can make different electric fields given different charges. It's actually kind of interesting to see how it all comes together. We're also going to be, and you can create lines of equipotential. And that's something that's something you can do too. And we'll learn about potential very soon. Okay. So anyway, moving on. Electric field due to a point charge. Now this is pretty straightforward. Electric field due to distributions are a little bit more complicated. Like if you talk about electric field from a wire or electric field from a plate or anything like that, you're going to have to use calculus. But for this first thing that we're going to do here, okay, the electric field due to a point charge. So let's just say I have this positive charge right here. Let's call this Q, and I'll put a little plus on it. Now, first of all, you know that electric field from this is going to point out. That's straightforward enough. Okay. Now we want to figure out what the force, okay, what the electric field itself. We have the direction, we want to get the magnitude. Well, now the electric field is equal to the force per unit charge. So if I put another little positive charge out here, I'll call this little q, also positive. If I wanted to know the force between these two, the force would equal 1 over 4 pi epsilon naught. Okay, it's fine for now. Q, big Q, little q. And we'll say that this is the distance between them, r, between their centers. Okay? And the distance between them would be r squared. So if I want the magnitude, okay, the force, the electric field will equal the force per unit charge. Okay, so I want the electric field created by this big charge Q. Could I figure out the electric field created by this Q? Absolutely. It'd be the same thing except for I'd be dividing by big Q. Okay, I want the force per unit charge created by this charge Q, so I take that one away, I divide by it, and I wind up with 1 over 4 pi epsilon naught, big Q over r squared. So in general, the electric field by a point charge is equal to 1 over 4 pi epsilon naught, okay, Q over r squared. Okay. Again, this becomes more helpful when we get into start using plates and we use Gauss's law. Now, the electric field from several point charges. Okay, if we put a whole bunch of point charges together, electric field from several point charges. So if I have Q1, Q2, Q3, dot, dot, dot. And I have a point P right here. Let's just say that this is a little charge, Q positive. And I've got R1, and R2, and R3. And that's going to go on and on. You got radii and everything like that. Well, the force that would be on this charge here, the force that would be on the charge there would equal, I'm going to use K. K, Q, little q, over R1 squared. Okay, I'll call this Q1. So that's a force due to 1. And this is going to be a vector. So we're going to use a term called r hat. That just means in the direction of r. Okay? Everyone uses r hat. We've always used ijk. This is essentially using polar coordinates. Okay, where you're just using you're worried about the direction that r is in. We call this r1 hat. Plus, all of this really does is make it a vector. It says that in the hat's direction. Okay? Actually, I should probably write this in too. So it's going to be the force on 1 plus the force on 2 due to 2 plus the force due to 3. Okay, dot, dot, dot. This is just what we talked about earlier when we were doing superposition. R2 squared, R2 hat. Okay, remember the hat means it's a unit vector. Plus K, Q3, Q, over R3, squared, R hat. Okay, so I mean, don't worry about all that for right now. All I'm trying to do is show what this winds up being. So if I want the electric field, it's going to be the force on Q divided by Q. So this is just going to wind up equaling F1 divided by that Q plus F2 divided by that Q plus F3 divided by that same Q. So my electric field, okay, also works by superposition. E1, it's one of the definitions of having a vector. E2 plus E3. The electric field is at any particular location is the electric field at due to 1 plus the electric field due to 2 plus the electric field due to 3. Okay, so we're just adding those up. And I was just setting these forces all where we're actually using Coulomb's law to kind of set it up. So we can actually set this up as kq1 over r1 squared plus kq2 over r2 squared plus kq3 over r3 squared. And we have to add them as vectors. We can't just add them as numbers. We don't add them arithmetically. Okay? We add them vectorially. Okay? And we have to take that into account. Now, this leads us to homework question number 2. A, B, C, D, and E. It's not terribly hard. I want to know, let's just say that in each of these cases, okay, the basic setup is this, and because I don't want to have to redraw some of the things that are going on. Okay, I've got 4 charges. Q1, okay, Q1, Q2, Q3, Q4. Okay, and we're going to look at this point P. That's not a charge that's in the middle. It's not a charge, it's just a location. It's point P. This distance right here, okay, is R. Okay, all these lengths are equal, so all the R's are equal. All these are the same R. And all those R's are equal to each other. Additionally, okay, we're going to say that the magnitude of Q1, the magnitude of Q2, is the magnitude of Q3, is the magnitude of Q4, which will equal Q. Okay? Now I might put a 2Q in there, okay, but all of these are equal to this value Q, unless I put a 2Q. So it's a multiple of Q at that point. Now, all right, I want to know what is the electric field in the center for each arrangement. A. Positive Q, positive Q, positive Q, positive Q. B. I want to set up Q, Q, Q's. Positive. Positive, positive, negative, negative. C. Positive, negative, positive, negative. Positive, negative, negative, positive. Okay. D. Positive, positive 2, so it's twice the amount. Positive, negative. That's where we gotta hit it. Positive, positive. And then have to do the opposite sign. So negative, negative, positive 2, negative. All right, I want to know what the electric field is in terms of K, Q, and R. So in terms of K, Q, and R. Okay? You also need direction. So that's 2 homework problems. Then in the book, there are 3 problems to do as well. 3, 7, and 11. So chapter 22, I believe it is. In addition to the 2 problems I gave you, chapter 22, 3, 7, and 11. Okay. I want you to work on those for homework. In addition to the problems that you were already supposed to turn in at last class, which, it's chapter 22, that a lot of you didn't get done. Okay, I will be checking that you do the 2 problems I put on the board, plus those 3 questions, in addition to the problem set that you already had. All right, well, I leave you at that, and I will see you on Friday.